So this is our third lecture in Chapter 5 on transient conduction. This topic right here, the lumped capacitance, most important. Make sure you master it. You guarantee an exam problem on it, either for this exam or for the final exam. We also had the highly mathematical, well, we skipped the generalized lumped capacitance, but we had the highly mathematical, what happens if I really want to solve for the temperature as a function of location and time, not just time only. And in a slab as well as in radial systems, that would be the temperature as a function of radial location, cylindrical or spherical, and time. Challenging. We had like a one-term solution when the Fourier number was greater than 0.2. But today, we move into semi-infinite solids. What does it mean that you have a semi-infinite solid? You know, it's like the whole world cut in half and you're looking at half of it. So let's jump into it. So you have the half, here's a big solid. We cut it in half and then we focus on this side. So we have a coordinate system, x, running from 0 off into infinity. It doesn't go from 0 to L, it goes from 0 off into infinity. That's the semi-infinite part. You have three different boundary conditions that we'll deal with. The first, we'll deal with the specified temperature. So somehow the boundary temperature at x equal to 0 is changed from, let's say, let's plot temperature coming up this axis, temperature. This would be the initial temperature in the material, and it's uniform temperature everywhere. At all locations x, it has the Ti for the initial temperature. But if you have a specified boundary temperature, it's like the surface temperature is abruptly changed to a value Ts. Boom. It's changed, and now there's going to be heat flow into the semi-infinite material. And so after maybe a millisecond, the temperature profile looks like this. It didn't heat up deep into the material, but it's heating up starting at the surface and going into the material. And then maybe after 1 second, then after 5 seconds, after 10 seconds. And we're going to solve for that one. But we're also going to handle the case. We're going to spend a lot of time on the specified surface temperature boundary condition and solve that problem. But we're also going to deal with the second case and the third case. The second case and the third case are where you have a specified heat flux. So let me kind of sketch it. Here's our semi-infinite material. X is running that way. The initial temperature everywhere, it's Ti. And then what do we have? We have like a laser, Q double prime at the surface, pushing heat into the solid. And if that's a constant, just like Ts turned out to be a constant, we're just going to abruptly change it there and leave it there, then we would have flow of heat coming in. And you would do Fourier's law, and so you have conduction heat transfer, and the slope would always be the same because it's always being pushed in. All right. And then the last would be the convective boundary condition. So you have the semi-infinite material. Maybe I'll sketch it over here. And you have a convecting fluid specified by a temperature T infinity and an H. So we'll introduce our coordinate system running x goes from 0 out to infinity. And then we think about temperature. Everywhere, it's uniform temperature. All three of these cases have the same initial temperature profile. It's just uniform, semi-infinite material, all one temperature. And then if you change and now expose it abruptly to a fluid, what's going to happen is the surface doesn't get all the way to the fluid temperature out here, but somehow the surface temperature may be this value after 1 second or 1 millisecond, maybe this value after a few more seconds, maybe this value after a few more seconds, until maybe after a long time, it's very close to the surface temperature, but maybe it's still propagating into the semi-infinite material. So we'll deal with these two cases later. Let's focus only on the specified surface temperature boundary condition. So again, we have a clean idea, or clear idea of our geometry. X is a coordinate system. we're going to be interested in solving for the temperature as a function of all locations x. X goes from 0 to infinity, as well as all time. So we're solving for temperature as a function of two independent variables, space and time. Okay, T initial, our initial condition, I'm resketching it, and then abruptly change to TS, and then we watch the propagation of the temperature profile as time goes on, increasing time. Okay, what would be our governing differential equation to solve for the temperature? Well, first of all, would it be an ordinary or a partial differential equation? Should I put an ODE down or a PDE down? What's the clue? Why is it a PDE? Why is it a partial differential equation? Because there's two or more independent variables. It's a function of space and time. And so what does our partial differential equation look like? It basically is our heat equation. It's the second space derivative of temperature. And then we'll have the first time derivative. And then you could put a rho c there and a k there. Or it's a little more compact, if you bring the k over, right? And if you bring that k over, what happens to this? 1 over alpha. So this is a good way of writing it. 1 over alpha times the time derivative. Now I try to be careful. I'll get a little sloppy later, but this is the symbol for a partial derivative, meaning it's a function of temperature's function of more than just one independent variable. All right, so if I have two space derivatives, how many boundary conditions do I need? Two boundary conditions. If I have one time derivative, how many initial conditions do I need? One. All right, so let's go ahead and write out our initial condition. Maybe I'll do the initial condition first. So we'll say that the temperature at any location x, but at time equal to 0, is equal to the initial value, the specified initial temperature throughout the semi-infinite material. That's our initial condition. Now, a boundary condition is that the temperature as x goes off to infinity for time greater than 0 is equal to the initial temperature. Deep, deep, deep into the material, it's still Ti. Well, what happens if I have a finite length and this thickness is given? Won't eventually the temperature at this location L start changing? Yeah, but now we just changed. We don't have a semi-infinite problem here. Now we have a finite slab problem, and that we've already analyzed. So we're not looking at x only going up to L. X can go up to infinity, and because of that, far away, deep into the solid or infinite material, it's T initial. The other boundary condition is that you have that the temperature at x equal to 0, hey, that's at the surface, isn't it? Yeah. At time greater than 0, right after that abrupt change, that has now changed to a new value. It's changed to TS. Well-posed mathematical problem. I am so glad that you've had so many classes in calculus and engineering analysis, because deep in those textbooks and in those classes, you've solved problems like this. Now, this is a funny one, because the strategy for solving this PDE is to break it into an ODE, bust it into an ordinary differential equation. Okay, so how are we going to do that? Well, they looked for a long time and they said, you know what, this temperature profile right here looks a whole lot like this temperature profile right here, which looks a whole lot like the temperature profile right here. It's as if they're just stretched a little bit. It's like they all have the same shape, but they've been stretched a little further and a little further and a little further. So it's like they're stretching the x-axis to accommodate the different future times. So they introduced the concept of a similarity variable. What? Look, at some geniuses worked it out long before I ever thought of it or even could learn about it. And it's the similarity variable is a single new variable, which is a combination of both of those independent variables, space, x, and time, square root 4 alpha t. Can you see that that's just a new variable? Sure. It has x in it and t in it. So what I can do now is transform the governing differential equation from a partial differential equation into an ordinary differential equation. Let me just kind of show you what this looks like after I do a lot of work, hard work. It looks like this. We'll have the second derivative with respect to our new variable, our similarity variable, equal to -2 similarity variable times the first derivative. How did that come about? Again, 3 dots and a 4-letter word. A lot of work. All right. But what you do, it's not that hard, is you can sit there and say, the temperature is a function of x and y, x and t, like this. But we're going to look for temperature as a function of eta, which is a function of x and t. See that? So it's like temperature is a function of eta, and then eta is a function of x and t. So what we do is we say, well, before I had the first derivative with respect to x, well, that should be a different type of derivative, a partial derivative. Well, that's the derivative of temperature with respect to eta times the derivative of eta with respect to x from calculus. And you just have to do that with time, and you have to do it twice with eta and x to get the whole thing transformed. And the difficult thing is you bring out this 2 eta right there. So it's kind of, this is now a ODE, but it's still a challenging ordinary differential equation. Okay, I have to transform my boundary conditions and initial conditions. If I take a look at this, t at all x, it's time equal to 0. Just focus on this equation right here. If I let time equal to 0, what does eta do? That's like temperature at eta goes off to infinity is equal to t initial. Okay, what about transforming this condition, which is a boundary condition? Well, you do the same thing. You say, well, x goes off to infinity. Well, look at our similarity variable. What's eta doing if x goes to infinity? You get that the temperature at eta goes to infinity is equal to t initial. Do you know what? Those two, the initial and the one boundary condition, collapse to only the same condition for my ordinary differential equation. You have to have the collapse of conditions, otherwise this wouldn't work. But these are the same condition. Okay, then the last one is a new condition, so you need two unique conditions to solve the second order ODE. So this collapses to the temperature. Well, let me change color here. Temperature at eta equal to 0 is equal to Ts. Wow, that was pretty hard, but guess what? I am still very, very happy that you have taken a whole class in calculus and differential equations, because dot, dot, dot with another 4-letter word work, a lot of it, you get a solution. And here's the solution, that the temperature minus Ts, that's a constant, remember what Ts is, divided by T initial minus Ts is equal to, so it's like a temperature, a ratio of temperature differences, is equal to ERF, what's that? Error. Hey, professor, you have an error here. Yeah, no, it's the error function, and the error function is a function of my similarity variable eta. That's the solution. Professor, I'd like to see you work that out step by step. No. Sorry, don't have time. It could probably work it out pretty slick with Laplace transforms, but there you go. All right, so now last time we talked about our old friend, the Bessel function, and you said, I never had a friend called the Bessel function. And before that, we talked about your old friend, the hyperbolic tangent. You say, I don't remember any hyperbolic tangent and all this. Well, today, guess what? Your old friend, I never remember the error function. What is this? Is this a math class or a heat transfer class? Sometimes we don't know the difference. So we have to familiarize ourselves with the error function. Let me jump to the next slide. Okay, clicker question. What are the SI units for the similarity variable eta? Eta was defined as x divided by the square root of 4 alpha t. Is it dimensionless, seconds, inverse seconds, meter, or inverse meter? All right, there's two ways of solving this. You can just say, well, what are the SI units for x meter? And then you come over here, you say, but I have the square root of 4 dimensionless. What about this alpha? Meters squared per second. What about time? Seconds. So the seconds cancel. I have the square root of meter squared. That's meter over meter, and it's dimensionless. Okay. The other thing you can remember is, in engineering, if I have e to the minus x or something like that, or e to the minus b or something like that, what would be the units for x or b if I'm really going to exponentiate it? Dimensionless. Somebody says the sine of x or the sine of b. What are the SI dimensions for x or b if I'm thinking about taking the sine or the cosine or the tangent? Well, they need to be in radians or degrees for your calculator, but what is a radian? Length over length. Dimensionless. It's dimensionless. So a lot of times when you see these functions, they really take inputs that are dimensionless. Just remember that, okay? All right, so our error function, ERF, it's a function of, let's put x if you want to, or eta, let's put eta right there, is 2 divided by the square root of pi, the integral from 0 to eta, exp, the exponential, of minus u squared du. Okay, let's go slow. How about the 2? That's a constant. I like that. I'm glad there's a 2. How about a pi? No problem. I understand those parts. You take the rest of the equation, okay? No. Let's keep going. We have an integral, but where does eta show up on that right-hand side? The only place it shows up is the limit of the integral. This seems like a very unfair function, doesn't it? But it is a function nonetheless. And then we have the exponential of minus u squared du. What do you call u in this term? The smart variable of integration or the dummy variable of integration? The dummy variable of integration. I mean, you could have put x there or tau there or any other symbol. So when you switch around in your textbook, you'll see maybe they use a different symbol than u at this location or that location. But that's the statement of what the equation is for that error function. Here's the Gaussian error function. Sometimes they'll tuck the name Gaussian in front of it, but that's the same thing. They'll say Gaussian error function or just error function. Here is the reminder of the equation. I know you may have to squint to see it, but they use v instead of u. And there's the upper limit. That's a function of w. Okay, great. Not eta, w. But they put it here as w. W runs from 0 all the way to 0.3, 0.4, 1. Here's continuing double. It's like w is like 3 columns of w. Where do they end? W is around 3. So all the action has happened for the error function going from 0 to out to 3. The error function, it starts at 0 and goes and goes. And what would you say that it's, if somebody said, give me the error function at 5. Oh, the table doesn't go that far. Well, come on, extrapolate a little bit, right? What would it be? 1. Yeah. So The error function is like the hyperbolic tangent, goes between 0 and 1. Kind of not that exciting. All right? And here it is analytically. In the earlier class, I said, pull out your calculator, see if you can evaluate the error function at blah, blah, blah. Only one person did it, and they coded up the integral, and they had their calculator do the integral, and they got it. But otherwise, your calculator doesn't have the built-in error function that I know of. Check your calculator and see if it does, but I think if you wanted to do a numeric value, you would use the integration, and you'd code up the integral. All right. The error function is sometimes called the blank error function. Is it called the quadratic, the complementary, the Gaussian, the normal, or the Helmholtz? So what we'll do is we'll pull back and take a look, and it's right there, the Gaussian error function. Now, there's a thing called the complementary error function, and it's discussed somewhere, and they'll put ERFC of W. What's the C mean? Complementary error function. I don't know why that's just the way they put it. Instead of CERF, they put ERFC. Okay. And that's equal to 1 minus ERF of W. 1 minus the error. So instead of going from 0 to 1, it goes from 1 to 0. Okay. So this one we want to grade, and it was the Gaussian. All right. In a semi-infinite material, the temperature is often a function of space and time, and it's solved in terms of the error function, the Gaussian error function. What is the value of the error function at x equal to 10? Is it 0.01 or less, 0.1, 1, or 10 or greater? The error function, if I plot it as a function of x, ERF of x, it starts at 0 and it goes off. About 3, they stopped the data on the table because it was already close to 1. But it went almost as a straight line right in here, and it just, that's what it was. Kind of not that exciting. It really wasn't that exciting of a function. So the best answer was perfect. It's about 1. Because if I go out here, to 10, it's 1. All right. Okay, we have the similarity variable has been introduced. Eta has been introduced. I can't remember what the similarity variable is. Can you? So that similarity variable is just something that you almost have to just know what it is or memorize it or refresh your memory, but it's x divided by this 4 alpha t in this book. Somebody says, hey, I looked at a different book. It's x divided by 2 square root of alpha t. Which one is it? Same thing, same thing. Sometimes they put the 4, sometimes they put the 2. You just have to pay attention. It's the same thing. So very good. Let's solve a problem. We have a thick slab with the thermal diffusivity alpha is equal to 1.39 times 10 to the minus 7 meters squared per second. And it has a thermal conductivity K of 0.58 watts per meter degree C. It's at a uniform temperature. T initial is 5 degrees C. The surface temperature is suddenly changed to Ts equal to 20 degrees C. Determine the temperature at a depth x equal to 5 millimeter and time of 20 seconds. Okay, how are we going to solve for that? How about I pause? You will have to have written down the equations that I shown earlier. You'll have to calculate an error function or the input to the error function, eta, the similarity variable, and then actually use that to evaluate the error function at that magnitude for the similarity variable. Let me see how far you get. Okay? So basically we had a analytic solution for the heat diffusion equation in the semi-infinite material with this boundary condition such that the temperature can be unraveled to be the surface temperature plus the initial minus the surface times the error function evaluated at that magnitude of the similarity variable. So if I knew the similarity variable, which was x divided by the square root of 4 alpha t, all of these are known. The x is 0.0, where is it? Depth of 5 millimeters, 0.005 meter. And then 4 times alpha, 1.39 times 10 to the minus 7 meters squared per second. And then our time was 20 seconds. And we take the square root, and that eta becomes 1.5, 1.499, something like that. Now, you have to go to the table. I think the table's around here. And if you went to 1.5, you could read off a value of 0.96611. Or if you had a calculator, some are able to actually perform that integration, this integral right here. I know the equation sheet gives us this equation, does it not, for the error function? Does the equation sheet give us the error function equation? So you could program it in, and it's a finite integral then, because you're integrating from 0 to 1.5 of e to the minus u squared du. All right. So you get that that value is, so essentially the T is equal to the surface temperature 20 plus T initial 5 minus 20. Notice that's negative 15, so don't mess up on the sign, times a 0.96611, and the temperature at that location and time turns out to be 5.5 degrees C. That's what you had? Very good. Okay. All right. Very good. Thank you. Surface heat flux. So think about it. If I have the effect of abruptly changing this surface temperature from Ti to Ts, and the temperature profile is going to be changing like this in the solid as a function of time. Do you think that was accomplished by having a Q double prime at the surface equal to a constant, or is it changing Q double prime at the surface? You can actually solve for it now. We can solve for that surface heat flux. So what we do to find Q double prime at the surface, which is going to be a strong function of time, is we say, go back to Fourier's law. How does Fourier's law help? Well, it says that Q double prime is equal to minus K, the derivative of temperature with respect to space evaluated at x equal to 0. Isn't that Q double prime S? Yeah. We just got that analytically. So all we have to do is take the partial of, with respect to x, of my temperature, which was Ts plus Ti minus Ts, error function of eta. Is this a math class or a heat transfer class? I want to know. Well, to get the Fourier's law, I need that derivative with respect to space. So would that be the derivative of temperature with respect to eta times the derivative of eta with respect to x from calculus chain rule? Yeah. Now, this one is probably the easiest, because wasn't eta equal to x divided by square root of 4 alpha t? If that's true, what is the derivative of eta with respect to x equal to? Yeah, that's the easy one. 1 over the square root of 4 alpha t. So that one we've got. This one's the hard one right here. It's the partial of temperature with respect to eta. Because if I come down here, I have the partial of temperature with respect to eta is equal to the partial of all of this with respect to eta, which becomes Ti minus Ts times the derivative of the error function of eta with respect to eta. Okay, people that look at that, remind me again, error function of eta is equal to 2 divided by the square root of pi. The integral from 0 to eta, it's the upper limit. That's where the eta is in this equation, of e to the minus u squared du. How am I going to differentiate that function? Pardon? We're going to do what? Pause and take a minute. All right, we're going to pause, take a minute. All right, I'm going to get a clean sheet of paper here, insert, just from memory, not prepared to talk about it. But you can have I is a function of x is equal to the integral of a of x to b of x, integrand, let's say f of tau comma x d tau. That's as complex as you can get. And if you wanted to get the derivative of I with respect to x, you have to realize that the lower limit in this integral is a function of x, could be, and the upper limit is a function of x. And the integrand not only has a dummy variable that's being integrated, but could also be a function of x. This is the most complex that I know of. And I forget whose rule it's called. Is it Leibniz rule? Is it? Did anybody get out and look on the internet?
Well, I searched it and I came up with beer tourism, so I don't think it's Leibniz either.
It is? Oh, look at that. I remembered something. All right, and it's pretty complex, and I'm going to move on. But for here, it's just the upper limit. And so the derivative right here, this just turns into 2 divided by the square root of pi, e to the minus eta squared. That's what it is. And so that's pretty simple. Now, if you're going to evaluate this at the surface, where is x? What is the value of x at the surface? 0. See, that would be x equal to 0. What's the value of the similarity variable eta at the surface? 0. I mean, look at the definition of eta. So guess what? If I come down here and I say I want to evaluate this at eta equal to 0, that becomes 2 over the square root of pi, e to the 0, 1. We're done. All that work, Professor. You're joking me. Yeah, this is tough stuff. But the bottom line is q double prime at the surface is equal to minus k. You pick up this ti minus ts. You pick up the 2 over the square root of pi. And you pick up 1 over, I'm going to put the 2 square root of alpha t from this part right up here. Comes down. So the 2's cancel. The pi can come inside the square root. And this minus sign, you switch the order of those. And so I'm going to scoot down. Here's the final bottom line. Q double prime S is equal to K. The higher temperature Ts minus the lower temperature T initial divided by the square root of pi alpha T. Look good? All right, somebody says, what was alpha defined as? Wasn't it K divided by rho C? Is that true? Okay, we're going to use that in a minute, but this is the big result because you can simplify it a little bit more with that alpha. But that's the big result. We already knew how to take the derivative of the air function. We just did that. Okay. You have the same slab, thermal conductivity, thermal diffusivity, the same uniform initial temperature of 5 degrees that suddenly changed to 20 degrees. Determine the heat flux into the slab at the time of 20 seconds. How would I do that again? I would use that equation, Q double prime at the surface is equal to K Ts minus T initial divided by the square root, divided by, square root of pi alpha T. That's all it is. Plug and chug at this point. So we pick up that it's around 2940 watts per meter squared. That's at a time of 20 seconds, isn't it? Let me ask you this. At a time of 10 seconds, okay? At a time of 10 seconds, is the Q double prime at the surface going to be less than 2940, equal to 2940, or greater than 2940, all having units of watts per meter squared? So, answer A, B, or C. So I know that we just calculated it at 20 seconds. At 20 seconds, it's 2940 watts per meter squared. At 10 seconds, what is it? And you really don't need to rerun your calculator if you just think. Right? It's just a thought, conceptual. So the consensus is that it's greater than, and you could verify it if you're real fast on your calculator by putting time. Well, the only thing that's changing is time. And time, you're going to divide by the square root of time. So if you're putting in a smaller time, right? How about this? Somebody says that time equal to 0.00001 second is Q double prime, the same thing. Less than 2940, equal to 2940, or greater than 2940. Let's just play with that one. There you go. So basically, there's a little bit of a singularity. What does Q double prime at the surface do at time equal to 0? Well, I'm going to do 1 over the square root of 0. It's like infinity. But that's the result of having this mathematical instantaneous change in the surface temperature. You're going to have an infinite flux to accomplish that. So don't worry too much about the singularity. All right, this is where I like to have you pull your hands out, get your fingers up to the same temperature. Sometimes your extremities are cold, so rub your hands a little bit, and then take your fingers and touch things. Find a piece of wood around you. Find the cloth maybe of the seat. Find the plastic around you. And then find the metal, usually in the frame of the seat. And touch them. And then get a sense of how hot or cold they feel to you. Get your fingers back up to temperature. Then touch the next thing. Then touch the next thing. And then answer this clicker question. After you've found the metal, found the wood, found the plastic. We don't have carpet, so use the cloth of the seat in this room. Which one feels the coldest to your touch? Let's see how people voted on this. Wow. So now let me ask you the question. What's the air temperature in this room? Let's say 75 degrees F. All right. What is the temperature of the plastic in the seat in this room right now? Not the one you're sitting on, the one adjacent to you. Nobody's sitting in it. Is it higher than 75 or lower than 75 or equal to the air temperature 75? 75. How about the metal in the room? The metal that you touched, was its temperature the same as the air temperature? Or was it cold? No, you had the feeling of being cold, but it wasn't cold. It's actually 75. Everything you touched was essentially the air temperature in the room. So why does some feel cold to our touch and then some not? That's right. So basically, you have two semi-infinite solids coming into contact. If you leave your fingers on the metal for a long time, the sense of how cold that metal is slowly goes away. If you leave it on the wood for a long time, the sense of the difference in the temperature will slowly go away. But if you take a semi-infinite material and put it in contact with another semi-infinite material, call this semi-infinite material A, call this B, let A be your finger, and let B be the metal or be the wood or the plastic, what you're going to find is you are living, you are not dead yet, you are at a higher temperature than the air temperature in the room. There's little metabolism, etc. And it's not the same as your internal temperature of around 98.8 degrees F, 37-ish degrees C, but it's higher than the air temperature, or the 75. So this temperature of A initial of your finger is higher than the temperature B initial. So if you tried to use this axis here as the temperature axis, you'd kind of draw it as coming in here. This is high, and way over here, this is low. Now, when you bring them into contact, something happens at that interface such that the interface jumps to a temperature. That interface temperature could be TS, could be close to TBI, could be close to the wood or plastic or metals temperature, or it could be up here and it would be closer to the finger's temperature. And that's what you're sensing. In your fingers, you do have things that measure temperature. It takes a little bit of time to communicate with your brain, but it's a pretty good little temperature measurement device, right? You have other parts of your body, maybe your wrist, maybe your lips. If your mother checks to see if you had a temperature when you were a child, how did they do it? Often with lips or with the wrist on the forehead, things like that. Those are devices to measure temperature. Your fingers do the same thing, so it's just as good. So, how does the math that we just learned in the physics of the heat transfer apply to this? Well, you do a small little control volume right here. And because I've drawn it where what's on the left is hot, there'll be a flow of heat out of A. And that'll be per unit area out of A. And guess what that has to equal? The flow of heat into B. So it's like Q double prime out of A has to be equal to Q double prime into B. Not only at the first millisecond, but after the 20th millisecond and the 50th, it's at all time. And when we look at it, that interface temperature goes to TS and stays there as long as the approximation that this is semi-infinite and that's semi-infinite. Your finger's not semi-infinite, and the metal's not semi-infinite, or the plastic's not. But for a short, brief time, it is. And you leave it there long enough, then it senses how thick that metal is, or how thick the plastic or wood is. So we just worked out, what did we have? We had this equation where we had the thermal conductivity of A. We had the, I'm going to get rid of the negative sign. So the temperature of the A far away minus the surface temperature, that's a positive delta T driving the flow of heat out of A, divided by the square root of pi alpha of A time. Did I get that right for the flow of heat out of A? And then likewise into B, the thermal conductivity of B, temperature of the surface minus temperature of B initial, that gives me the right sign. It's the surface is higher than B far away, divided by the square root of pi alpha B time. And so both sides, the flow of heat is proportional to 1 over the square root of time. That's why this comes out. Again, I'll repeat, this is an approximation when they're semi-infinite. In a lot of engineering applications, things are in contact for brief times. And there can be significant heat transfer even for those brief times of contact. So there can be some very thin things that can be approximated very well by the semi-infinite material approximation. The pi's cancel. At this point, what we can do is go and say K divided by the square root of alpha is K divided by alpha is K over rho C, square root, right? So this K over the square root of alpha is just simply the square root of K rho C. It's a grouping of terms. Look at, if you find another textbook, they may name that a new property, and they'll give it another name. We have enough names of new properties, okay? Just let it be K rho C square rooted. All right, now, what you can do is you can take and redo the math using that, and you can get that the surface temperature is equal to some fraction times TAI plus some fraction times TBI. And the two fractions are going to add up to 100%. If you've done a few engineering problems all the way back to statics and that, you see this sort of pattern evolve. And so for this one, it's going to be the square root of K rho C, all for material A. This is the square root of K rho C, all for material B. The K and the B, rho and the C are all for material B. And then you divide it by the sum. Maybe I'll do it this way so I don't have too much to rewrite. You just divide the whole thing by the square root of K rho C, all for A, and then the square root of K rho C, all for B. Such that, again, this is a fraction just like this is a fraction, and they sum up. Sometimes it'll be 10, 90%, meaning it'll be closer to the other temperature. If they're 50-50, well, then it's going to be in the middle of those two temperatures. Or it could be 90-10, and then it's closer to the other one. Anybody seen this one? No? It's a movie, so we're going to have a little fun, I think. Oh, I have to jump over here, don't I?
Schwartz created a slight breach of etiquette by skipping the triple
How many
dare
people have
and
seen this
going
movie?
right for the throat.
All right.
Over here. How many people never saw it? There you go. Homework for the weekend. No, for the Christmas break.
Well, go on, smart ass, and do it. I'm going.
Flick's
That's not a
spine
wood
stiffened,
pole.
His lips curled
That's
in
a
a
metal
defiant sneer.
pole.
There was no going back now.
They paid him extra. It's a fake tongue. How many people have reached into the ice tray to get some ice out of the freezer, and the fingers get stuck? Or it's even worse, if you have a metal, aluminum type of tray before the plastics, you would grab those, really be stuck. They're going to help them, don't worry. They won't abandon them. Yeah, they'll help them. Our book doesn't give us anything about the material properties of the human tongue. But you know what? With the internet, you can do a pretty good job. And you could find a K, and you can find a C, and you can find a rho needed. And then we'll just get some metal. Let's get some carbon, low carbon steel. And once we have those, we can apply the equations. And we can say, hey, what temperature is that human tongue? It's in the mouth, close to the brain, right? You're healthy, you're alive, 98 point something, it's around. You would not think that a tongue would get frozen anything. It's a 37C. But when the 37C infinite, semi-infinite material comes in contact with the pipe, the metal pole, semi-infinite, and maybe that pole is negative 10 degrees C, all you need is that surface temperature of the contact with a little moisture on the end of that tongue. Just like a little moisture sweat on the fingers when you grab something frozen, metal, or a cube, ice cube in the tray. All that has to do is get below the magic 0C, because that little film of water freezes. And it freezes very fast, and it's like, you can't, you try this, don't do it. Take your tongue to a metal and then get it off fast. You're not going to beat that one. Your reaction rate of, let's say, I don't know, 20 milliseconds or something, tongue on, tongue off, is not going to help. Even your finger on, finger off, you're not going to beat it. It's going to freeze. It's going to go to TS. If it's below 0, you're stuck. Yeah, you may rip a few. That's right. So if you did this for the tongue and the properties I've shown, it's -6. Again, it's just equations we just shown. It's just this right here, that surface temperature. I put in the 37, we put in the -10, but that weighting makes it go much closer to the metal. Hence, you get it frozen. Look at the thermal conductivity of the tongue. Look at the thermal conductivity of the metal. That's a factor of about 120. That's huge. Now, the rho and the C, they go as a product. So you have to look at the product of those. Let's go ahead and make the multiplication. What is rho C for this one? And then what is rho C for the tongue? Okay, one is a measure of how it conducts heat. The other is a measure, the rho C is the sluggishness, the thermal inertia. 3.625 times 10 to the 6. The rho C down here is 3.407 times 10 to the 6. So it's not a difference in the rho C, it's a difference in the thermal conductivity. Do you think they can expand this and do it for the specified heat flux? We've spent all this time on the specified temperature. Let's go ahead and answer this clicker question. Either case A, case B, or case C is describing how the temperature varies if I have a convective boundary condition. Again, it's over here is where you would have that boundary condition applied. So is it A, B, C showing a profile for convective boundary condition? Well, sometimes I wish the fonts were a little bigger, but here's a big hint. What is that? T infinity. Yeah. And then notice that the surface temperature is changing. So basically, case C is the convective boundary condition profile. If I do this one, what is the one for the constant surface heat flux? This is a constant surface heat flux. It's like a laser being is equal to a constant. Well, when you have a constant heat flux at the surface, that means the minus k dt dx at the surface. And what they're trying to do here is have the same slope. So isn't B the best answer? Why did we not get more right on that? Here are all the analytic solutions. And I'd encourage you to solve a few problems with the convective as well. I had a problem worked out for the convective. You can use this equation, but you're going to have the complementary error function, etc. Or if you do have that problem, there's a plot that actually is for that problem. So I think you probably have a homework problem using that too. But it's just evaluating the parameters and looking it up. As a last comment, this is one of my favorite sections. Why? Because it's so applicable. You've probably frozen your fingers on stuff. Okay. Yeah, you have. But there's something else that I always try to help students be very practical. Christmas is coming up. Gift-giving time is coming up. It's not that far away. Some of you still have grandmothers that are living. I'm going to help you right now. Big help. I can give you a hint for a Christmas gift that will be surprisingly good. Maybe a little pricey. This is what it is. And this goes with this section of the textbook. When your grandmother needs to get up in the cold winter and go to the bathroom in the middle of the night, there's a little bit of sitting down on the toilet seat that can be a little bit of a shock. Some of them actually put little foam or things on there for that. In Japan, years ago, somebody told me, oh, I visited Japan, the greatest invention since sliced bread. Electrically heated toilet seats. So if your grandmother lives up north, she doesn't know about this. This will be a great surprise. To do that, okay? So there's my big hint for you if you are looking, gift-giving idea.